Engineering preliminary design presentation, and this is the team Varuna, and the DTL is Ryan Salee, and he will be leading the presentation. But before that, I would like to have the reviewers introduce themselves.
Hello, my name is David Krantz. I'm a graduate here, and I work modeling and simulation in the industry.
Greg Bunting, I'm visiting from Sandia National Labs in Albuquerque. I do finite element work.
Mike Fabian, mechanical engineering propulsion.
All right, welcome everybody. We are Varuna Hydro, and we are going to walk you through the preliminary design of our hydro turbine. I am Ryan Salee, the design team lead, Neil Patel, and Eric St. Germain. Here's the overview of our presentation. We're going to lead off with an introduction, followed by our requirements, then our component design, as well as our testing procedures, instrumentation, budget, followed by conclusion and recommendations, and then we will open the floor up to questions. Our design requirements, as per the RFP, are to design, build, and test a turbine that can convert the kinetic energy of moving water into electricity. We will generate at least 100 watts of continuous DC power with the flow, once the flow requirements have been met of 6.5 feet per second, as well as at least 5 feet of depth for full submersion of the turbine. Our requirements are to build and test the turbine with a $1,000 budget. We must produce at least 100 watts continuously with a flow velocity of 6.5 feet per second or greater. And the turbine must be durable enough to perform a 10 to 15 minute test in the Verde River. The components of our turbine are as follows. The red ones are called out in the picture. They include the blade, hub, nacelle, and structure. The black components are not shown on that illustration because they are within the nacelle. For our blade design, Neil Patel will walk you through that.
Good afternoon, everyone. I'll be talking about the blade design. So for the blade design, the requirements are that it must be able to convert kinetic energy in water into power. It must be able to rotate in water at a velocity of 6.5 feet per second. It must have a dovetail connection, and it must be printed with a high-resolution waterproof material. The constraints for the blade design are that it cannot break under stress from water currents, and it must be able to print within the dimensions of the 3D printer, with the length of the blade being allotted 15 inches and the length of the dovetail being allotted 1 inch. So before we move on, as you can see, this is the assembled rotor in CATIA. The top red box indicates the blade. There are 3 blades. The center dashed box indicates the 2-piece hub, and the bottom arrow points to the location of the dovetail connection. So to design our blade, we use the blade element momentum theory, which is the combination of the blade element theory and momentum theory. It analyzes the blade shape to calculate the rotor's ability to extract power from water. For the design approach, the team must evaluate and choose certain design parameters. The reasons we chose to use the blade element momentum theory is because I have prior experience with this theory and approach. Also, most modern turbine blades are designed by using this theory. So the design parameters for the blade element momentum theory are the rotor radius, water velocity, number of blades, tips-to ratio, angular velocity, airfoil selection, angle of attack, number of elements. So the total radius of the rotor is 16.942 inches. It is the combination of the length of the blade, which is 15 inches, and the radius of the hub, which is 1.942 inches. The approximate sweep area of the rotor rotation is 902 inches squared. Our turbine will have a cut-in speed of 6.5 feet per second. The cut-in speed is the minimum speed of water at which the blade is considered operational. The team chose the number of blades to be 3 because we researched into pre-existing hydro turbines and due to ease of manufacturing. As you can see in the table on the right, the number of blades 3 gives a range of the tip speed ratios indicated by the variable lambda from 4 to 5. We just took the average of the tip speed ratios to be 4.5. A tip speed ratio is the ratio of angular velocity at the tip to the speed of the water. For electrical power generation, it is recommended to have a tip speed ratio in between 4 and 10. Our tip speed ratio is closer to 4 due to lower angular velocities in water. So angular velocity is the rotational speed at which the rotor rotates. In the picture, the rotor is rotating to the right and is indicated by the variable for angular velocity omega. Our calculated angular velocity is about 200 RPM or 29.52 feet per second. We calculated this number by using the radius of the rotor, tip speed ratio, and the speed of the water, and conversion factors. This is important because we need to use the angular velocity to find torque and power. Moving on to the airfoil selection, the team chose to use NACA 6409 airfoil. It is sketched on the figure to the right. The maximum camber is at 6%, maximum camber position is at 40%, and thickness is at 9%. The number of points we chose to use is 61. The number of points when connected form a spline. The reasons we chose this airfoil is because it was already provided on an airfoil database, and it has a more hydrodynamic shape than other airfoils in the sense that it generates a higher lift coefficient than thicker airfoils. For the angle of attack, it was determined first by the Reynolds number. We calculated our Reynolds number to be 450,000. The selected data set from the airfoil database had a Reynolds number of 500,000, so it was close enough to use that data set to find the angle of attack. The data set consisted of the coefficients of lift and drag, and which were directly related to angle of attack. So the team chose the angle of attack to be 4 degrees because the team took the lift to drag ratios for each of the angle of attacks and found the first maximum lift to drag ratio to be 4 degrees. The first maximum lift to drag ratio was 121. So all those design parameters are put into a MATLAB code, and from the MATLAB code that ran 20 iterations for the 20 elements that we used for our blade, resulted in midpoint radius, chord length, and section pitch angle. The midpoint radius is the location of each element's cross-section. The chord length is the length of cross-section from the leading edge to the trailing edge, and the section pitch angle is the angle between the plane of blade rotation and the chord line. The figure on the right does not show the section pitch angle, but shows the chord length and midpoint radius, and it indicates as each of those sections are elements. Then the team generated about 1,200 coordinates for all 20 elements in Excel. The chord lengths determine the size of the airfoils. Then the team used a macro to export the coordinates and splines into CATIA. These splines are automatically spaced out based upon their midpoint radii. The CATIA model was done by twisting each of the elements, or splines, at their respective section pitch angles. Also, the team created an oval shape at the 0th element for the dovetail connection. So as you can see on these two figures, on the figure on the left, the leading edge, clearly shows the chord lengths, with greater chord lengths toward the base of the blade, where the dovetail is, and becoming smaller toward the end. The larger surface area toward the base of the blade allows for the blade to extract more power from the water. In the figure on the right, the trailing edge shows the steep angles from the base of the blade gradually decreasing toward the tip. The steep angle in the beginning at the larger surface area provides a higher lift. For the dovetail design, the requirements are that the dovetail must be the connection piece to the hub for the blade. It also must be printed with the blade as one part. The constraints are that it cannot be longer than 1 inch, and the 3D print, it must fit inside the 3D print made size when printed with the blade. So the dovetail shape is a trapezoid. We chose this because it will not slip out of the hub once inserted, and is common amongst turbine blades. As you can see in the picture, top picture is the shape of the dovetail, and in the bottom picture is the CATIA model of the dovetail attached to the blade. Also, the material we chose for the blade and the dovetail is a closed source ABS plastic. We chose the closed source over the open source because it has a higher resolution. The interior structure of the blade and dovetail is completely solid. Now onto the hub design. For the hub design, the requirements are that it must hold all 3 blades, it must have simple assembly steps, it must have simple disassembly steps so that the blades can be removed easily. It must rotate with the blades, and it must be able to connect with the shaft. The only constraint is that it cannot cover any part of the blades except for the dovetail. The design choices for the hub is that it has 2 pieces, the top part and the bottom part. The material of the hub is a closed source ABS plastic as well, and it is a solid interior structure. The hub top consists of the nose cone and the top plate. The nose cone shape was decided to be a cone because it provides a hydrodynamic flow in the sense that water can flow around the nose cone much more efficiently than a flat plate. The top plate has 3 holes for the connection by bolts to the bottom plate, and the top plate also has a flat underside to sit evenly on the bottom plate. The hub bottom consists of a bottom plate and then cylinder. The bottom plate has 3 holes for connection by bolts to the top plate. Also has 3 dovetail cutouts, not all the way through the bottom plate, so that the dovetails can fit inside, and has a shaft cutout opening in the center. The end cylinder, which is behind the bottom part, is there because it has to ensure the stability for the shaft, and has 2 holes, which one is shown, the other cannot be seen, for the screws to lock the shaft into place. This is our printed model of the blade. And now I'll be passing off to Eric Sanchman.
Thank you, Mayor. So I will be going over the nacelle design. The requirements for the nacelle are that they have to house the generator in the gearbox. It needs to be waterproof so it does not short out the electrical components inside. It needs to have easy access for installation of these electrical components, and it needs to be 3D printed to reduce cost. The constraints for the nacelle is it needs to accommodate a rotating shaft attached to the structure, and it cannot be larger than 12 inches cubed according to the 3D printer bed. The overview of the nacelle is that it is 8 inches cubed of outer dimensions, 5.6 by 6 by 5 inches inner usable dimensions. It's a 3D printed part of using open source ABS plastic, and it's a 2-piece design. The face of the nacelle is going to be the interface point between the rotor and the nacelle. It's going to have an inset design for the hub to protect the low-speed shaft from the environment around it. And in order to make this interface watertight, it's going to have a mechanical seal that is designed for a rotating shaft. The top plate of the nacelle is going to be removable. This is going to help for that easy access to the generator compartment. There's going to be 8 1/4 inch diameter holes, and we're going to have to use the silicone caulking to make that interface watertight as well. The bottom of the nacelle is going to have 6 1/4 inch holes. These are going to be used to attach the bottom part of the nacelle to the overall structure, as seen in the right picture above in the orientation. The back of the nacelle is where the 8 gauge generator wire is going to exit, and in order to make this interface waterproof, we're going to have to use a cut-to-fit liquid-tight grommet. The interior design of the nacelle is going to be 5.6 by 6 by 5 inches of usable space. As you can see in the picture above, the 8 1/4 inch diameter holes to secure the top plate in place, the 6 1/4 inch diameter holes to secure to the structure, and it's going to have a generator mounting platform. The generator mounting platform in the interior design of the nacelle is to raise the generator off the bottom of the nacelle to align the high-speed shaft with the low-speed shaft of the rotor. Onto the structure design for the hydro turbine. The requirements for the structure is that it needs to support the rotor and nacelle assembly, stabilize the hydro turbine, elevate the hydro turbine to mid-river depth, and be able to be submerged. The constraints for the structure design is it needs to be movable by 2 people, detachable from the nacelle, and have an adjustable height when the river depth changes. So the overview for the structure is overall it is 3 feet tall. It can adjust to a max of 4 feet. It attaches to the nacelle. There is a locking pin release for the adjustments, and it has a weight plate to help keep the structure submerged underwater. The main legs for the structure are 3 feet tall, made out of 1 inch steel tubing, that's 1/8 inch walls, and they're welded to the top plate. The picture on the left shows the front legs of the structure having a 30-degree angle between each other. This is to help design the structure in a tripod configuration. The picture on the right shows a 70-degree pitch from the front legs and the back legs to the mounting plate. It is also to help get the tripod structure. The main legs are welded to the mounting plate, with the front legs being 2 inches offset from each other, and the front legs being 4 inches offset from the back leg, again for the tripod structure. The interface between the structure and the nacelle has the 6 1/4 inch diameter holes to secure it to the nacelle. It is made out of a 4 by 6 inch steel plate that's a 1/4 inch thick. The adjustable leg extensions for the structure will get the structure going from 3 to 4 feet in 6 inch increments. They are going to be using a locking pin release in order to hold those legs in place. The legs can be done independently of each other, and the adjustable legs will be made out of 5/8 inch steel tubing with 8 inch walls. The weight plate to help keep the structure submerged is going to be 19 inches by a 14 inch triangle. It's going to have a lip of a 1/2 inch thick to keep sandbags on the plate, which will help the structure be submerged. Onto the generator and the gearbox selection. The requirements for the generator are that it has to be a 12-volt DC, and it has to produce 100 watts continuously. It needs to have an 8-gauge wire lead and be a compact size so it can fit inside the nacelle with the gearbox. The requirements for the gearbox is it needs to be compatible with the selected generator, able to increase the ratio between the low speed and the high speed shafts. The constraints for the generator is it needs to be water resistant, it needs to be DC, and it cannot have a maximum over 40 amps continuously because it will end up frying our charge controller. The constraints for the gearbox is the size limitation to fit inside the nacelle with the generator along next to it. It has to have a high enough gearing ratio to produce power, but not too high that it oversteps the motor. We've selected a generator and a gearbox. The generator and the gearbox came together as a 12-volt, 2,500-pound DC winch. We are going to remove the winch part of this motor and just keep the motor and the gearbox. They are weather resistant. and they go up to 1.05 horsepower. I do not currently know the gear ratio for this gearbox because we have not tested it yet. We will do that in detail. However, we do know that it's a planetary gearbox, and we're buying this from Tractor Supply Company. On to testing of our parts. We're going to do a control test where we fully assemble the nacelle and all waterproofing needs. We're going to submerge the nacelle in the water of a pool, make sure that it is fully waterproof before we introduce any electrical components. That way we're not frying the electrical components before the full test. This will also help us be able to test all individual components such as the structure, find out exactly how much weight is needed depending on how deep of water that we're getting into, and we'll be able to test the entire system combined together. Our real world test is going to be in the Verde River. We're going to need a minimum water depth of 6 feet, a maximum water depth of 12 feet. Anything over 12 feet, we will not have visibility in order to submerge our structure. We also are going to need a minimum water velocity of 6.5 feet per second. This is due to our low cut-in speed. However, for the past 7 years at the Verde River in Paladin, Arizona, the water velocity has been double our low cut-in speed, up to as much as 27.89 feet per second. On to Ryan Sleep.
All right, I will be discussing our electrical system. The primary purpose of our electrical system is to collect test data so that we can optimize the blade design as well as the gear ratio to increase power production. Our secondary objective with the electrical system is to store the electrical power that is generated by the generator. The components of our electrical system include a charge controller, a battery, a dump load, and the appropriate instrumentation. Our charge controller is essentially a switching power supply that will charge the battery, and once the battery is fully charged, it will divert the power to a dump load, and it monitors the battery voltage to select between the two sources. The model that we've selected is a Xantrax C35 charge controller. It's commonly used for wind turbines and is applicable and is a good application, or is a good choice for our application. The battery we will be using is a 12-volt lead-acid battery. It's a common automotive battery. They are readily available and inexpensive. It can be charged from a varying power source, which is what we have. And once that is fully charged, the power will be diverted to our dump load. The dump load will either be a resistor or a heating element. This will dissipate the excess electricity that is produced by the generator once the battery is fully charged. We did consider other options such as light bulbs or tools. The problem with other dump loads such as a light bulb is if the light bulb burns out, the excess power has nowhere to go and it will fry the charge controller. For instrumentation, we will be collecting our data just before the charge controller because the charge controller does use some power and we would like the most accurate data that we can collect. We have not selected a DAC yet. We are hoping to borrow one out of one of the labs on campus. The instrumentation that we intend to use is a tachometer to monitor the speed of the generator shaft, a voltmeter to log the amount of voltage that is produced from the generator, as well as an ammeter to log the amount of current. This data will be analyzed to define the desired range of RPMs that we would like the generator to be at to maximize power production. Once we have our data, we will reach our target RPM range by adjusting the gear ratio and optimizing the blade design. And for our budget, our 3D printing costs included two types of 3D printing. One is the Dimensions printers, which uses a closed source ABS and is more expensive, but prints with a higher resolution. That is used for the blades. And we are also using an open source ABS that is less expensive for the nacelle and hub because we do not require such a high resolution for those parts, and we can save money that way. The raw materials that we need for the structure, we need low carbon steel tubing. We need 2 types of that. The 12-foot 1-inch tubing will cost us $60, and 6 feet of the 5/8-inch tubing will cost us approximately $25 from McMaster-Carr. For our shaft, for the hub, we will be using 6061 aluminum that we will have machined to accommodate our unique geometry. And for our plates in the structure, we will use A36 steel. We will buy 1 large plate that costs $105, or $205 rather, excuse me. And that will be cut so we can get the 2 plates that we need out of it. This is a list of the products. I've discussed some of them. Some of the ones that I have not discussed include the mechanical seal, which we will get from McMaster-Carr, as well as the wire grommet. We will be using 50 feet of 8-gauge wire that is weather resistant. That is so we can run all of the instrumentation and charge controller from the shore of the riverbanks because we don't want to expose it to water. According to the charge controller manual, the 8-gauge wire allows us to do up to a 30-foot run with only a 3% voltage drop. And we also will have a circuit breaker to safely stop our test. And we also need the silicone caulking to waterproof our nacelle. Here's an overview of the budget. We plan to source as much of this as we can on campus and hopefully get donations such as the winch that we will use as our generator. Everything priced out minus the instruments so far is about $900, and once we source materials on campus and get donations, we expect to be well underneath our budget. For conclusions, our blade design uses a NACA 6409 airfoil. It is 3D printed out of closed-source ABS plastic, and it has a press-fit dovetail to prevent movement within the hub. The hub has a unique oval-shaped hole for the shaft. This is to reduce the pressure on the plastic and disperse it over a larger area. And it allows the blades to be removable so we can test different blades, and in the event of a breakage, we can swap that out and continue testing. The nacelle will be waterproof, and it has a removable side so that we can access the gearing and generator should we need to make any changes or swap parts out. For the structure, we will utilize low carbon steel tubing and plates that we will paint. Due to the short duration of our test, we do not anticipate any corrosion or problems with that material. We will have adjustable length legs to increase the amount of deployment areas that we can utilize for our test. And the structure also accommodates sandbags for anchoring so that it is more secure for our test. The electrical system includes a switching power supply to go between the battery and the dump load. We will be testing in the Verde River. We intend to test for 10 to 15 minute intervals, and the purpose is to collect performance data so that we can optimize our design. Our recommendations going into detail. For the blade design, we would like to create a thicker airfoil for more rigidity. And we will also adjust the design as needed so that we can reach our target RPM. The hub, we will hollow the nose cone to reduce the weight and decrease the cost a little bit. And we will also move the holes toward the center so they are not so close to the edge to ensure that the bolts do not break out of the plastic. For the structure, we will perform structural analysis to ensure that we will not have any problems with the turbine moving around during testing. And we also need to determine how much weight we need to add for the sandbags so that we know it's not going to go anywhere. For the gearbox, once we have performed tests with the motor to find the acceptable ranges, RPM ranges, we will determine the optimal gear ratio. For the generator, we need to create a mounting plate once we actually have it so that we can securely mount it within the nacelle. For our gearbox, we must determine the optimal gearing ratio, and then we can design it. Our instrumentation, we must select a DAC, and once we have a DAC, we can select the compatible instruments to collect the data that we need for our optimization. Our labor hours are as follows. We are 11% over the expected amount, and most of that is due to the significant increase in preparing for this presentation and getting our CAD models all prepared. We also put in a lot of time to get our parts 3D printed, and that is how we are 11% above our estimated total. I would like to thank Dr. Sean Wright, Dr. Brenda Haven, Dr. Matthew Haslam, Dr. Lance Traub, Dr. Young-Ho Lee, Professor Jim Helbling, Robert Graham in the Rapid Prototyping Lab, and Jim Weber, Laboratory Technician, for their help with our project. I would now like to open the floor to any questions.
For printing, you didn't run into the spool problem that one of our teams last year did, where they get partway through a spool and then start printing with a new spool?
No, they did not. However, they did not swap out gray for white filament, and we now have one gray blade. But that's not such a bad thing because we anticipate it being a little bit easier to see it rotating. So it worked out pretty well, I would
Okay,
say.
that's good. All right, I just know that the promised characteristics don't come through if they change it halfway through.
Yeah, we did actually print the blade in a way that had never been done before, so we got a little less resolution than we were hoping to do because of the angle that it had to sit at in the print bed. So that's part of the reason we need to redo for a thicker blade.
Okay, no problem. How are you getting your signal for the tachometer? Are you going to record it within your little nacelle, or are you going to try and get it to shore through your grommet?
We intend to have the instrument on the generator and run it through the grommet to shore.
Okay, I didn't know if you were going to record on site or on your or something.
Oh, no.
Okay, all right, just checking. Okay, and my last question is, okay, you said you're going to run for 10 to 15 minutes. How are you stopping it?
A circuit breaker, and we will be dropping it into the water on ropes from the bridge, which is why we have that picture in there.
Okay,
so we'll just pull it out of the
You
water.
just pull it out of the water, okay.
Correct.
Just want to make sure you weren't doing something crazy, like bicycle brakes or something weird. Okay.
No, not in the plans.
Right, I have a few questions as well. So I saw the 6.5 feet per second as a minimum speed of the water. What's the maximum?
That has not been determined yet because we need to test the motor so that we know RPM ranges, and then we will figure out our gearing ratio and we can figure out the maximum speed.
Yeah, and then the other kind of big thing to me is the structural analysis. Is you've printed your parts but haven't done the structural analysis. I don't know anything about the strength of 3D printed material, but do you have an idea of the force you're expecting, say at the connection, or the overturning force of the thing, or have you done that work and it just...
I believe those calculations are in the blade element momentum theory. I'm going to hand it over to Neil to answer that question.
For the stress analysis and structural analysis, we haven't done any calculations related to that. We hope to accomplish that in the detail phase of the project.
But you've printed your blades already?
Yes.
Okay.
All right, so I just have a few things. I think several of my questions were actually answered there in the PowerPoint. So you're sealing the nacelle.
Correct.
Do you have any contingency plans, if you will, for if water does get in there? Because from my experiences with water, especially moving water, it's very difficult to keep it out with so many open access areas. So I guess, how are you going to deal with that occurrence if it does happen?
I will hand that over to Eric since he is the design point on that.
So that is actually why we looked for a generator and a gearbox that is weather resistant. So there's some play on the safety of that. We are going to try our best with the nacelle, and that's why we're doing a control test in the pool without those electrical components inside. So we'll have to fully watertight that, then obviously open it up and make sure water has not gone in. We were going to use a small test such as an aquarium, but the deeper you go in the water, the higher the pressure, those seals might actually bust on us or the grommets. So that's why we're doing a pool, so we can get down to our depth like we would in a river. If it does end up leaking, we're going to have to go back to the drawing board and redesign a new watertight seal.
Okay. I guess the other question associated with that is with the wires. Electricity and water tend to like each other a whole lot. I guess my concern is with the wiring, is there's a big difference between wiring that's rated for underwater use and wire that's just okay handling some rain on it, I guess.
Yes, and Eric can answer that question.
So the wire that we actually selected, the 8-gauge wire, it has a higher diameter of insulation on it. It is meant to be water and oil resistant, since we can't find anything that is completely waterproof. It is water and oil resistant up to a certain depth, as long as, of course, the insulation is not scratched. And since it's going through that liquid tight grommet, and it's going to be in the nacelle, which we are hoping that it's going to be completely waterproof, that leads to the wire will not be exposed to any water.
Okay. I think that's all of my concerns, really. It sounds like a great project. You guys sound like you're having fun with it. And a good presentation.
Thank you, appreciate that. Yes?
I have a couple of non-technical questions. One is, you said that you had an RFP. Who is your customer? And number two, the name of your Varuna, how did you come up with the name for that, Varuna Hydro?
We do not have an actual customer for our RFP, and I will allow Neil to answer the question as to where Varuna came from.
So before we even started the project, we were deciding a name, and we knew we wanted to do a hydro turbine. So we came up with names of gods from religions, such as Poseidon, but that's an overused name. So I went to Hinduism and found the god of the celestial ocean, name is Varuna. So using that as our name, Varuna Hydro, indicates that we were doing hydro turbines.
Thank you very much, I enjoyed it.
Thank you.
All right, any other questions?